Hi everyone, my name is Franziska Böhnisch and I'm a researcher at the Fraunhofer ISAC Institute in Germany. Today I'd like to present my paper on surveying and systematically reviewing work in the domain of watermarking in neural networks. What was missing in this quickly developing field, by the time that I was working on the paper, was an overview on existing work in the topic. This is however important since more and more methods were starting to be proposed, then shown invalid by other work and then being redesigned. Many of the methods even operated in different threat spaces and solving slightly different problems, so they were increasingly difficult to compare for this reason. I therefore set out to collect approaches, systematize them and the general knowledge around them, and assemble different security requirements from related work and evaluate the schemes according to them. With this work, I was hoping to provide some guidance for someone who enters the field newly, or for researchers or people in industry who need to commit to a suitable watermarking scheme based on their use case, and also for researchers who are looking for an interesting entry point, for example in the form of shortcomings and open questions in the existing approach. My talk today will be structured as follows. I'll start with a little background on model stealing, then go over to evaluation criteria and requirements for neural network watermarking. Afterwards, I'll show the threat space and concrete attacks against watermarking schemes, and then give a systematic overview on existing approaches. Finally, I will provide an outlook on research challenges and perspectives. In model stealing, we can basically imagine two different scenarios. One is the white box and one is the black box scenario. As you can see in this figure, an attacker has direct access to a model in a white box scenario, and therefore model stealing might just be as simple as copying the model. In a black box scenario, the attacker does no longer have free access to the model or the training data, but can interact with the model over a very clearly defined API. Still, in this scenario, thanks to model extraction attacks, the model can be stolen. For this, the attacker just has to take some auxiliary unlabeled data, obtain labels from the original model, and then train a surrogate model based on the data of the obtained labels. One can distinguish between two types of model extraction: a fidelity extraction attack that can be considered successful if the surrogate model is very close to the original model and probably even does the same mistakes, and a task accuracy extraction aims at creating a surrogate model that solves approximately the same underlying decision task. The existence of both of these types of extraction are basically the reason why one needs to protect machine learning models with watermark in the first place. Like other digital media, watermarks in neural networks are a form of digital property protection, where we embed some identification information into the original model to claim copyright later. To be able to really do so, neural network watermarks should fulfill the following requirements. The first requirement is the one of fidelity, which means that the model should still perform very well on its original task and the watermark should not degrade its performance. When talking about robustness, we need to make sure that the watermarks are robust against removal, such that someone cannot just steal the model, remove the watermark, and thereby escape some ownership claims. Reliability means that watermarking schemes should exhibit a minimal false negative rate, such that if a model is really watermarked and a legitimate owner wants to prove ownership, this should succeed with a very high success rate. In integrity, we want to minimize the false alarm rate. So if a model is not watermarked, our watermark should not be seen in this model, and thereby we could avoid erroneously accusing honest parties with similar models of theft. Watermarks should exhibit a kind of large capacity that allows for the inclusion of meaningful data, such as the signature of a legitimate model owner. Watermarks should fulfill the requirement of secrecy, which means that the presence of the watermark should be secret and not be known to, or should not be detectable by some unauthorized party. When talking about efficiency, we mean that the process of including and verifying a watermark model to a model should be fast and not create large overheads. Generality means that watermarking algorithms should be independent kind of the dataset and the machine learning algorithm used, and thereby allow the scheme to be used in a broad context. In addition to these requirements here, one could also exhibit a wish for unique watermarks. This is useful when instances of the same model are distributed to different parties and the legitimate model owner, in the case of model stealing, wants to know which party was responsible. The requirements for unique watermarking schemes are the same as the ones for common watermarking methods, but extended by the two following points, namely uniqueness, so the watermark should be unique for each user. This serves to identify model instances individually. And secondly, such unique watermarks should be scalable, so the schemes should allow to be able to apply to many users, so that we can even apply it in a large-scale distribution of the target model. In my opinion, before now diving into the description of watermarking schemes and approaches, it is important to understand the attack vector against them. So, what attacker could possibly want to achieve and why they would like to do so. In my opinion, this helps to understand the design and the pitfalls of designing valid watermarking schemes. I've here listed the main classes of watermarking attacks, so when designing or choosing a scheme for a specific scenario, one should always have in mind what attack the scheme is supposed to protect about. In the best case, of course, it protects against all of them, but even though that might not be necessary in some scenarios. The weakest form of attack against watermarking schemes is the watermark detection, which is basically concerned with an attacker being able to discover the presence of a watermark in a stolen model. This might give the attacker, for example, the opportunity to then adapt the model's behavior in order to avoid watermark detection by the legitimate owner. Watermark suppression basically means that the attacker can prevent watermark detection, potentially even without the watermark being removed. So when the legitimate owner comes to verify the watermark, the attacker would just suppress the model's reaction on the watermark trigger from the original owner, and thereby the original owner would have no means to say if the model contains the watermark or doesn't contain it. In watermark forging, the attacker does also not need to bother with really removing the watermark, but instead can just pretend that the model is his own. This might, for example, be done by recovering the legitimate owner's watermark and claiming ownership. So if there's no binding between the watermark and the owner, this is possible. Or by just adding a new watermark that creates ambiguity concerning the ownership. Or by just identifying a fake watermark, so something that looks like it is a watermark even though it's not, and then the attacker can still claim and say, hey, this is my model because I've marked it with this, my watermark. In watermark overwriting, we have a setting where the adversarial knows the underlying watermarking scheme but has no knowledge about the legitimate owner's watermark. So the adversary can use this knowledge in order to embed a new watermark into the model, and thereby might be able to replace the original watermark entirely. If at the end both watermarks kind of coexist, we are in the forging scenario again, where there's ambiguity about the ownership. The strongest attack that we can see is the watermark removal. So instead of just suppressing the model reaction to some watermark or inserting a new watermark, an adversary might entirely try to remove the watermark from a stolen model. And once that the watermark is removed, actually no more ownership claims can be made against it. So some attacks that allow for this removal are fine-tuning or retraining or even pruning, rounding, compression, and distillation, just to name a few. So now that we know the threats that watermarking schemes have to deal with, we can look into them and into their design. To survey a broad range of watermarking methods that exist, I found it useful to create kind of a hierarchy that would put them into relation and group them semantically. Basically, this is the tree that I came up with. Since the time here is a bit too limited, in order to give every scheme that has been proposed enough attention and to discuss it in detail, I decided to stay superficial and explain the different branches of that tree rather than going into detail on the individual schemes. I invite you to take a look into my paper for thorough descriptions and tabular overviews on the given individual schemes. For now, here, iterating over these branches will give us the possibility to kind of see the bigger picture and to understand what challenges exist for every approach in the corresponding branch. So let's dive in. What we already see on the first layer after the root is that watermarking techniques can be broadly divided into two categories that I've been visualizing at the bottom of the slides. The first category is inserting the watermark or related information directly into the model parameters, and the second one is creating a trigger, carrier, or key data set, no matter how you want to call it. And this set consists of data points that evoke an unusual prediction behavior in the marked model. This unusual behavior can then be used in order to identify illegitimate model copies. The trigger dataset can be generated independently or based on the original training data, and watermark insertion can be done for both approaches during or after the training in a sort of fine-tuning. When inserting the watermark directly into the model parameters, the biggest issue usually lies in the prevention of watermark detection. So when we alter the model weights and parameters, this might usually not stay unnoticed. Instead, some distribution might change, which makes the watermark detectable to an attacker, and we would definitely like to avoid it. Additionally, and that holds for all leaf nodes under this left branch, is that watermarking should be done such that getting rid of the parameter changes or the new layers or some biases that we included by the watermark that leaves the model with decreased prediction accuracy. Otherwise, one can just take the watermark out and then have a good model even without the watermark. In general, what is nice when we introduce watermarks directly into the model is that most of such approaches give us the possibility to embed meaningful information. So instead of just showing that the watermark is there, biases in the parameters or in the new parameters or in the layers might incorporate the signature of the legitimate owner that binds the watermark to them. What one needs to keep in mind, though, is the verification scenario. So signatures that are only noticeable in the model and its weights, that might be of little use if we do not get white box access to them from the attacker, but instead just black box access. When creating trigger sets, the largest challenge usually lies in the fact that when we do that not very carefully, the model learns two different problems from two different distributions. One of them the original training distribution and one the watermark distribution. Thereby it becomes relatively easy to extract model information about the one without the other. Especially an attacker can just use task extraction to have a surrogate model that will still be very affected on the original task but not exhibit watermarks anymore. So we see that it's important to internally create kind of a relation between the both tasks. Another problem that arises is the choice of an adequate verification threshold. So in trigger-based watermarking approaches, the watermark detection relies on the model's reactions on the queries from the trigger set. If the agreement of the prediction on them to the original trigger set's labels overpasses a given threshold, this suggests the presence of the watermark. However, defining such a suitable threshold to identify a stolen model requires thorough tuning. So if the threshold is set too high, slight modifications in a stolen model might already be sufficient to prevent watermark detection, which violates the reliability requirement. But if the threshold is set too low, different models might just erroneously be identified as a stolen model instance, which violates the integrity requirement. Hence, the choice of this threshold also expresses a trade-off between reliability and integrity. An additional issue with trigger-based watermarks is the disadvantage for the scenario of public verification. So after the verification algorithm is run against the stolen model, the adversary will be in possession of this trigger set, which enables them to fine-tune the model on those data points and to remove the watermark. Hence, in order to do several verifications, the original trigger set needs to be divided, or there have to be several trigger datasets. But this class of approaches has a limitation due to the maximum amount of overfitting that a neural network can do on such triggers. When now looking into the leaf nodes of the right branch, we find adversarial example-based approaches. In these, the trigger set basically relies on adversarial examples in one form or another. And in this setting, one needs to take a special care since the robustness of the watermark might be easily violated. This is because adversarial retraining is nowadays broadly used to make models more robust, and this might just remove the watermark entirely while preserving accuracy on the original task. According to what we heard also about watermark requirements, a good trigger set is furthermore characterized by its uniqueness to the model and the model's prediction on it, in order just not to accuse honest parties of similar models of theft. We call that integrity, but since research has shown that adversarial examples might transfer well between similar models, this integrity might not always be taken for granted. And finally, adversarial examples in general also do not offer a link to the legitimate model owner, wherefore an attacker might just forge the trigger set easily in these approaches. In vector-based approaches, as the name suggests, we were training on a second task, namely the backdoor into the model. So this becomes possible due to overparameterization in neural networks. But the problem is backdoors and original tasks do not necessarily need to be linked anyhow by default, so therefore we might run again in this problem of training on two different distributions. When integrating watermarks into the original trainings data, such as like a company logo into a training image, We have the advantage that we can basically embed really meaningful information about the owner into the watermark, what we have before only seen in the watermarking approaches on the other branch, where we just insert the information directly into the model. But here basically we create a trigger such that they contain information. And then we train the model on the original task and on this created trigger set. However, also here one needs to keep in mind that the resulting samples with these watermarks or with this information about the original owner, they might have a different distribution, and so that the model would train on two different tasks again. The last branch to consider is the training the model such that its outputs activations on certain triggers will contain the watermark, either through just showing that a watermark is present, or even through the output activations given a signature of the original owner that we can then encode with an encoding scheme. So, but such approaches have a really high difficulty with generality, since actually for every model and every problem one might need to have a different encoding scheme. Furthermore, we should also not neglect the fidelity of the model on the original task, so when training it on something as difficult as just having something encoded in the output, we very much need to make sure that the accuracy on the original task is still given. Now that we have seen how watermarking approaches have been designed before, I suggest it's time to look into the future and give an outlook on research challenges and perspectives. What one needs to take in mind so far is that watermarking schemes are passive protections. This means that they cannot prevent theft, but just try its best to discover it, and different schemes do that more or less successfully in different scenarios. Some more active solutions have already been proposed, like issuing extraction warnings or creating methods like models that are so sensitive that they are really difficult to steal. So, in my opinion, integrating watermarking approaches into such more active protection scenarios is a really useful direction to pursue in the future. And a shortcoming of existing watermarking approaches is their so far kind of limited applicability. So most approaches are strictly limited to image data and only applicable in a classification case. Therefore I'm also particularly delighted that later today we see some exception to that. However, for many existing schemes, there is still the potential to extend the scope to other data types and other machine learning problems. Additionally, so far existing watermarking schemes are mainly applied and evaluated on rather small research datasets like MNIST. Therefore, the question of their scalability remains open. So approaches that require training with up to double the initial amount of data to incorporate the watermark might just not be applicable anymore. Thus, future work should therefore, in my opinion, assess the practical application of existing watermarking schemes to larger real-world data, and we would benefit in analyzing on a bigger dataset if the schemes still exhibit the properties that they have on the research datasets, like efficiency, reasonable trigger set size, or integrity. And finally, I think that this is one factor that I've already been personally experiencing in projects and in contact with the industry, is that once that we have no watermarking schemes that fulfill all the technical requirements we need, another challenge will still lie in their adaptation to real-world workflows. So especially the juridical or organizational workflows will have to be adapted in order to enable asserting ownership claims based on watermarks. At the same time, watermarking is evolving a lot, and also alternative ideas to intellectual property protection are emerging, such as, for example, having kind of proofs of learnings, which uses inherent properties of neural network training to prove ownership, and thereby just relies on the assumption that stealing a model is only worth it if this is related to less work than just training the model from scratch yourself. So with all these new directions opening up, I'm confident a lot that a lot of work can be conducted in the future to enlarge the potentials of watermarks for intellectual property protection neural networks. With this, if the time allows, feel free to ask questions. Otherwise, thank you for your attention, and please, if you like, get in touch after the workshop to exchange some ideas.